Chapter 6 demo. Problem number 1. A binomial experiment is conducted with the given parameters. Use technology to find the probability of X successes in N independent trials of the experiment. We don't take the word successes literally. So for example, if I'm doing a binomial experiment is one where there's just two possible outcomes. For example, tossing a coin. You want to know what is the probability of getting a certain amount of tails if you toss a coin 10 times. So if I'm counting the tails, then tails is considered a success. And then for it to land on heads, that would be the failure. But if I was counting the times it landed on heads, then heads would be the success and tails would be the failure. So the number of successes are the number of times you had the outcome that was desired, that you were kind of like counting. This is kind of abstract, so I'm going to put some meaning to this one here. I don't like this one as an example. Let me just answer some bogus answer, and then I want to generate a better one. So let me generate a new one. Give me a moment. So I have generated a new question. I selected view a similar question once I submitted a wrong answer. A binomial experiment has the following parameters. I'm going to put it in context. That's why I wanted a different one, just to make it easier in terms of I actually assigned a situation to this case here. But we are going to have to open StatCrunch, so get more help. If you ever need StatCrunch and it's not here, they probably mean for you to do it by hand, but or sometimes they forget to program it. So it would be a good idea just to maybe leave one of those windows open, or you can always just open a blank StatCrunch page. You can do that by going to the main page of MyMathLab and selecting StatCrunch. Let me share this window with you. So in 6 trials, the probability of a success is 40%. And what are the odds that you'll have less than 4 successes? So let's say for the next 6 days, the probability of rain is 40%. What are the odds that you'll get less than 4 of those 6 days rain? So you'd have to find the probability of 0. What are the chances of getting 0 rain days if the odds are at 40% chance, or 1 day, or 2, or 3? Not 4, because it doesn't say equal to 4. So we could have StatCrunch compute those probabilities for us. So we're going to go Stat, Calculators. We wouldn't go to Graph, it's not a graph. And we're going to go to the binomial. And binomial means there's only 2 outcomes. So either rain or no rain. We could do these probability experiments with more than 2 outcomes, but then it wouldn't be a binomial. Something like, let's say a basketball player has 3 free throws. What are the odds that he's going to make 0 free throws? 1, 2, 3. So that's including the 0, that's 4 outcomes. So it's not a binomial experiment because there's more than 2 outcomes. So we wouldn't be able to use this binomial calculator if that was the case. We'd have to do some other, in fact, we would have to do, well, I'll talk about it later. I think it shows up in a different example. Let's see, a little bit off here. Let me move my window here. Okay, so N is for the number of samples. In this case, we're doing 6 days of rain, let's say. And then P is for the probability or the chance of that occurring. In this case, in my problem is 0.4. You enter your values. And then what are the odds that it's less than 4? So strictly less, not equal to, and then I'm going to put 4. So here's the probability that it'll rain 0 days. Here's the probability of 1, 2, 3, 4, 5, 6. So notice that the odds of it raining 6 days is very low because there's a 40% chance. So the fact that it rains all 6 days would be surprising, right? If somebody said, oh, there's a 40% chance of rain in the next 6 days, and then it rains the entire 6 days, you would think, well, there was only a 40% chance. That's weird that it rained it. Why did they say 100% chance, right? Because our meteorologists are pretty accurate with today's technology and getting it pretty, on the money in terms of predicting rain. So we would be surprised because intuitively the odds would be very low of that happening. So a 40% chance, close to a 50% chance, would be a little bit less than half the days. Let's see, there's 6 days, so a little bit less than 3 days. And notice like the most likely to happen would be that it would be 2 days and almost 3 days too, but slightly less than 50%. So if it was 50%, then probably 3 would be the highest for my example, since there was 6 days, like half of those days it would rain and half of those days it would not if there's a 50-50 chance. But in this case, a little bit less than 50. So that's why the 2 days is a little bit more likely to happen. But in this example, they're saying, what are the odds that it either rains 0, 1, or 2, or 3 days? So we can add all these individual probabilities, and adding these 3 ends up being 0.8208. They want 4 decimal places. So if I multiply that by 100, that's like an 82% chance. So there's a very high probability that in the next 6 days, it's either going to rain 0, 1, 2, or 3 days. So it might rain 2 out of the 6, it might rain 3, it might rain 1, it might rain 0. But if we add those all together, like if you're betting money that it's either going to rain 0, 1, 2, or 3 days, you have an 82% chance of winning because any of those 4 outcomes would be winning outcomes. The only case you would lose is if it happened to rain 4, 5, or 6 days. Okay, so now we're going to put these individual probabilities for each day in this column here, but now we have a different problem. So now there's 9, let's say, days of rain. 9 days that we're going to be seeing if it rains or not. This time there's a 65% chance of rain. So more than half of those days is going to be the most likely average day. So that's 9. Between half would be 4.5, so between 4 and 5. The fact that it's a little bit higher than half, I'm thinking it's going to be 5 or 6 is the most likely outcome from all of them. So I'm going to do equal to 0 first. We're going to do them in order. So what are the odds that it'll rain exactly 0 days? Well, pretty low because you have a 65% chance. So if they say there's a 65% chance of rain in the next 9 consecutive days, and then it rains 0 days out of all of those 9 days, we would be surprised because we're like, wait a minute, there was a 65% chance of rain in the next 9 days and it did not rain not a single day. So if there's a 65% chance, the likelihood that it rains 0 days is really low. So 4 decimal places, that 7 is going to bump up this last 0 to 1. But if yours is a 5 or less for your example, then you might have rounded to 4 decimal places, 4 zeros. It doesn't mean there's a 0% chance. It just means it's so low to the nearest 4 decimals that it rounds up to 0. If this next one was a 0, then it would be 4 zeros. But it doesn't mean there's 0 probability. It's just that the probability is so small that it's close to 0, highly unlikely. But it's not exactly 0. It's sort of like the chances of winning the mega lottery. It's such a small probability, but there is a small probability. But the chances are that it's likely not going to happen. So you might as well think of it as a 0% chance of happening. But it isn't 0%. It's just so small that it's more likely not to happen than happen. Okay, so you're just going to go through this and do each one individually. I'll do it while you do it. And then we'll check the answers. Sometimes if you get it wrong, just go back and check it, make sure you're rounding correctly, that you use the right numbers. Sometimes there's a typo, you have 2 decimals, so it's easy to get the wrong answer just by a careless mistake. So go ahead and go through that. Okay, so if you are not done, then you could pause the video for a second until you catch up, or if you make a mistake and you're figuring out what to do. Okay, so part B, compute the average number of rain days in the next 9 days and the typical deviation from that center from the 9 days. So give or take one. So I would think my average is going to be near 6 because that was the most likely to happen. Maybe give or take a day or two, like 5 to 7. So maybe give or take a day might be the typical deviation from that center as to what the average number of days we would expect for it to rain, a little bit more than half of those 9 days. So yeah, we said between 5 and 6, but it looks like it's actually between 5 and 7 as to what the typical days are. So we need to find that center exact because it might be a little bit less than 6 once we do the formula. So this formula we would have to apply for problems that have more than 2 outcomes. We'll see if you have a problem like that, but basically you could have StatCrunch do that, put the outcomes in column 1, the probabilities in column 2, and then you can do what's called a custom calculator. But because this is a binomial and there are only 2 outcomes, then we can use the formulas that have been provided for us in StatCrunch. I also posted the handouts that you're allowed to use in StatCrunch. In Canvas, in terms of like the exams, there's two handouts. One of them is like the StatCrunch instructions, and the other one is, let's see if I can find it. The other one is like the, this is for the StatCrunch procedures. The other one is like for formulas. So there's one that you can use for your formulas, but I just kind of have it here, kind of showing here. So if you have more than 2 outcomes, this number 9, you do what's called a custom calculator. So you can follow these instructions here. So you can see like the box plot instructions and so forth. But we can just do the binomial one. So if I did the formulas for binomial, let me show you on the StatCrunch. This is for a previous course since I haven't set hours up, but there's these 2 first handouts for the course. You'll see something like this for your course. So here's the procedures that I just showed you. Here are the formulas. You would be able to use both of those for exams. Those would be handy to print out and just to have them on, next to you for the exams. Down. Oh, okay. So there's chapter 3 formulas. The only thing about this is like anything messy like this, we don't use, but this is nice for definitions. We don't even calculate the mean by hand, right? We have StatCrunch do it. So here's some definition. Here's the empirical rule. Those we have to do by hand. When we get to this chapter, we have to compute those by hand. Fences we have to compute by hand, but the 5-number summary, StatCrunch does it for us. In fact, here it says 5-number summary. It tells you what they are in case you don't know. There's chapter 4, chapter 5. Here's chapter 6. The mean is given by this, and then the standard deviation is given like this. But this is for like more than 2 outcomes. That's the one that they're telling us to use in this problem. But if I scroll down, this we don't use. Any complicated formula we don't use. But for a binomial, it's easier because since there's only 2 outcomes, we can just use these 2 short formulas to compute. So that's what we can do for this problem. So let me go back to our problem. And I guess technically we could do it the long way, but so if you do have a problem where it's more than 2 outcomes, then you would put all the outcomes in column 1. Just do it quickly just to show you in case something shows up. But this is not what we would do here. We would do the short formula. And then all those probabilities in the second column. If you want to try it, you can. Just pause the video and enter all your data. But I'm actually going to illustrate the short formula that was on StatCrunch. 194, 2716. 0.0207. Regardless, our average should be somewhere between 6, our mean, right? That's what we would think the center of this distribution would be. Okay, so where we had our stat calculators, instead of doing the binomial, we're going to customize it when there's more than 2 outcomes. Here we only have 2 outcomes, so it works for any number of outcomes, but we usually just apply this if there's like more than 2 calculators. So the values are in variable 1 and the weights in variable 2. So my outcomes are in column 1 and the probability of each outcome, which are considered the weights here, is in column 2. And then we just compute. It gives me the same diagram as before. Oh wait, this is not the one. Let me close this. Let's try that again. Calculators, custom. Select variables 1, 2. Compute. It's over here to the right. That's why I lost it. Here we go. All right, so the mean is 5.85. So it is really close to 6. Ignore this. It's highlighting everything to the left of 6. But and then it typically deviates by 1.4 days. So yeah, like close to 1 day, right? Remember I said the typical values seem like give or take a day. So that standard deviation is like you would come up with a window as to what the typical days are. So like 5.9 days, give or take 1.4 days will be, we can make a little window between 2 values where we can expect would be the typical rain days under these circumstances. So that gives us the answer, but we're actually going to do it a different way. So let me put these answers for now, because in part C is the actual formulas that we're going to use. So round to 2 decimal places, 5.85, it's already in 2 decimal places. And then the typical deviation to 2 decimal places, give or take 1.43 days. Let's see how, if we put it in context, it makes a little bit more sense instead of just saying, okay, these are X's, these are P's. What do they mean? Who knows? Okay, so they're saying that for binomial experiments only, when there's only 2 outcomes, yes, rain or no rain, we can use this little formula, multiply the number of n, the sample size, I should say, by the probability of, or likelihood of that happening. So I don't know if this has the calculator. Oh, good, it does. Okay, so we have the sample size n, which in my case is the number of rain days, times the probability of each rain day, which was 0.65 for this particular example. So see how we get the mean with just that simple calculation instead of doing everything I did over here. But again, that only works for experiments that only have two outcomes or binomial experiments. So we call those binomial. Otherwise, it would just say construct a probability distribution. But if it's going to be a binomial one, they'll let us know, which means we can take these formulas. This one says multiply n and p again, which is 5.85 times 1 minus p times 1 minus 0.65. So the way that would look like, let me put it over here. So the way that would look like would be 1 minus p would be 1 minus the probability 65. And if I did that on the calculator, it's 35. So it's like the probability of a failure. If there's a 65% chance of rain, there's a 35% chance of no rain. So these are the yeses and these are the no successes. 65% of a success, which is rain, and then 35% chance of a failure, no rain. So we're going to multiply the sample size. I already have it here as 585, but let me do it again. The sample size, which was 9, times p, the odds of this happening is 65 times, 65, which was the 5.85. And then I'm going to multiply that now by 1 minus p, which is the probability of a failure. And then that's just the inside. And then I have to take the square root of that. So let's see, is there a square root? Here it is, square root of that answer. And it gives me a lot of significant digits. But if I went around it to 2 decimals, it's 1.43, which is the same answer as before. Now, if we can use technology, then technically you can use either method. So if you like one or versus the other, it's fine. The only thing is that if they don't give us the raw, it's faster if they don't have us, here we have it computed, so it's easy. But if this is the only question, we don't want to construct this, it would take too long. So it's better to use the shortcut formulas. And then now draw the graph of the probability distribution. Do you remember what yours was? If not, remember how if you closed it, it should be over here in StatCrunch, results 3 hidden. So here's my binomial calculator. I did it twice, but let's just click on one of them. So here it is again. So I'm just matching the diagram. The only reason they put these little blue dots is so you can visually see where it ends, because it's kind of hard to read here. So notice it's kind of roughly symmetrical too, if we're talking about shapes. Okay, so I need to choose the one where 6 was the highest. I guess the only one that shows us is D. So this one is not close. Sometimes there's 2 diagrams that are close in terms of choosing the correct one, and we have to be careful. And then I said this one seems pretty symmetric, but if yours is slightly skewed, then I don't know, it's a little bit skewed to the left, but does it say roughly skewed? Let me see. No, it just says skewed. It seems like it tapers off a little bit to the left, but see, if I saw something like this, I would say roughly symmetrical. So don't hit check answer. Let me do mine first to see if I agree with the publisher. Yeah, see, if this was real life, I would say that's pretty symmetric, but the fact that it does kind of trail off to the end, they're going to want left skewed. So sometimes it's a guessing game as to what they think. But if we are going to say it's left skewed, it's slightly skewed to the left. It's not really obvious. I guess you could kind of see it in my picture a little bit. The one they drew, let me go. Oh, when I went back, it does a new one. I can't go back to the previous one. In the picture, it seemed like it was a little bit skewed. More than this in this diagram. So if I was basing it on what my math lab, it is a little bit more clear. Okay, so the third example, according to a study done by Nick Olson of Otago University, Wellington, the probability of a randomly selected individual who will not cover his or her mouth when sneezing is 0.267. Suppose you sit on a bench in a mall and observe people's habits as they sneeze. Complete the following part. So this is a very casual type of experiment. If you don't want to see this, you can open a new data table, but not there. It's okay. So I'm going to close mine because it's not the same one. So Not going to help me any. Or if you do get more help, there's you can open it here as well. Okay, which I think is what I'm going to do. And then let me share that again with you. Using binomial distribution, what is the probability that among 16 randomly observed individuals, that's the sample size, exactly 7 do not cover their mouths with sneezing? So the key word here is that it is a binomial distribution. So we can go to our binomial calculator. So stat calculators, binomial. And then we just have to figure out what all these values are in this case. So n is the number of how large the sample size was. And then, so in this case, they're telling us in my problem that there were 16 randomly observed individuals. So however many people were observed. And then the probability of, according to some study, the odds that a person is not going to cover their mouth is 0.267. So read carefully. It's not the odds that they will cover their mouth. It's the odds that they're not covering their mouth. So we're just counting the people that are not covering their mouth. So in this case, a success is anybody who didn't cover their mouth, because that's what we're counting. And a failure would be anybody who does cover their mouth, because that's not what we're counting. So we have to be kind of a little bit careful here. What are the odds that 7 didn't cover their mouth? So exactly means equal to. Didn't say more than 7, less than 7. So that's, here are the odds. I guess in a group of size 16, the most likely outcome will be 4 people out of every 16 people that won't cover their mouth. But the odds that 7 of them won't cover their mouth more than the typical is kind of low, 6%, because typically we would expect 4. So the odds of 7 of them not covering their mouth is, it looks like only like a 6.8%, almost a 7% chance of that happening. But they want it as a probability, so as the decimal version of this. So most answers they want will be as decimals. So occasionally they want the percentage. Mine's a 9, so I'm going to push that to a 6. So just be careful. Sometimes students are will put percentages when they should put probabilities, or vice versa. Again, using this distribution, what is the probability that among these 16 people, less than 3 do not cover? So now we're going to do less than. It didn't say less than or equal to 3, so strictly less than. So there's this one, which would be less than or equal to, or this one, which is strictly less than. So there's 2 options there. Make sure you choose the correct one depending on how it's worded. So what are the odds that less than 3? So it's these 3 combined, which is like a 15.8% chance of that happening. So my next digit is a 9, so that I'm going to have to change that 79 to 80, since I have to add 1. Now the trick question is part C, because they're saying using the binomial distribution, would you be surprised if after observing these 16 people, less than half covered their mouth? So now they're changing the situation when sneezing. So now it's a different type of binomial experiment, because now we're counting how many people are covering their mouth. So this changes. So if there's a 26.7% chance of somebody not covering their mouth, then 1 minus 0.267 is the probability that somebody does cover their mouth. What would that be? .733. Those are the odds that somebody, for my problem anyways, is going to cover their mouth. Now, the nice thing about StatCrunch, sometimes if you put it in here, it'll do it for you. So if I just put here 1 subtract the 0.026, it'll do the 0.733. Okay, so then well, we've been surprised that less than half. Okay, if there's 16 people, then that would be, half would be 8. So then we're going to do, what are the odds that the number of successes is less than 8, less than half? Compute. And then no or yes, it would be surprising because the probability is. Let me put the probability in here. So I need 4 decimal places, 1, 2, 3, 4. And we can decide whether that's unusual or not. Okay, anything less than 5% chance of happening in the statistics world is going to be unusual. So let's say there was a less than a 5% chance of rain, then you're going to say, oh, the likelihood of it raining is really low. And then all of a sudden there's like a downpour all day. We would be surprised. That would be an unusual result. So usually probabilities that are less than 5, we consider them to be an events that if they do end up happening, we'd be surprised by that. And we would say, oh, that the odds of that happening weren't likely. So that's unusual for that to have happened. So when we're thinking about unusual events, then we compare it a lot of times to 0.05 or 5%, unless the problem states otherwise for a particular. So in this case, since this one had about a 1.2% chance of happening, then, and let's say it did happen, that if I observed 16 people, less than half actually covered their mouth when I expected 73% of them to cover them, that would be in a surprising event. So yes, for me, it would be surprising because this probability is less than 5%, which is the cutoff for something to be considered unusual. But if yours is more than 5%, then you would answer the opposite. No, it would not be surprising. So let's say my probability here would have been 70%. No, that wouldn't be surprised if there was a 70% chance of happening and then it happened. Well, yeah, the likelihood of that happening. If there was a 70% chance of rain today and then it rained, you wouldn't be surprised by that. That would not be an unusual event. Okay, so that completes the demo for 6.2.